Good evening, everyone. Thank you so much for being here. I appreciate it. Without further ado, Chris Althemus has already given my title, so I will proceed. I'd like first to thank the engineering geology group of the Geological Society of London for this incredible honor, and also the 10 sponsors for this evening whose names are listed here, and Tracy read them out earlier. But thank you very much to those who provided sponsorship. I'd like to dedicate this lecture to my PhD supervisor, Dr. Everett Hook. He was the second Glossop lecturer in 1998, and his talk at the time was entitled Putting Numbers to Geology, an Engineer's Viewpoint. And I thought there were two really, there are lots of great quotes in his talk, but I think two of them really stood out to me in the context of what I'm going to talk to you about tonight. The first is, assigning numbers to geology requires a delicate balance between the commonly held opinion that geology cannot be quantified and the over-optimistic view that every physical quantity can be described in precise mathematical terms. In reality, many geological characteristics cannot be quantified precisely, and intelligent guesses based upon experience and logical arguments are the best that can be hoped for. He also said at the end of that paper that the responsibility of the design engineer is not to compute accurately, but to judge soundly. So that was from his 1999 publication from that presentation. So in 2018, he was interviewed by Geostrata for a series called Lessons Learned from GeoLegends. And at this point, he said, as technology improves, I see us taking geological observations and observed rock mass properties, plugging them into a model, and seeing what's likely to happen in large, complicated rock masses. Geological observations could be much more detailed and factual as well, like with Lidar measurements, so that statistical properties of discontinuities and intact rock properties could be incorporated into the models. And that's what I hope to show you tonight, the work we've been doing in this area. This would be a huge advance over the empirical models currently used, and that was published in Geostrata in 2018. So the problem I'm talking about tonight is this. I work mostly these days on rock slopes, and the rock slope failure events that we're dealing with are very often complex. They involve often several stages of activity, and warning signs cannot often be detected in advance, no matter how much we try. And so if you watch up here, this is a place where a rock slope failure is occurring onto railway tracks. They had stopped traffic on the tracks because there'd been a pre-existing failure that you could see in the foreground. Then a subsequent failure occurs, and you can see how that rock mass is fragmenting, falling into small pieces. And if you keep watching, there's some very small telltale events that are continuing to ravel from that slope. And in a moment, you'll see the final bit of this failure occurring. And so what we've done up till now, and you'll see later, we've been modeling rock falls as single events of a single lump. And you can see most often that the behavior we just saw is in fact what's generally observed. So rock slope instability is not new, of course, and thinking about it is not new either. So the assessment and analysis techniques, the workflows we work with are well established. And on the slide, you see here on the left side, classification schemes that have been developed around the world to think about classifying cut slopes. This example is from Larry Pearson from the States, and that was actually discussed by Dr. Hook in 1999 paper. And on the right side, you see a much larger active slope. In this case, this is a 1.5 billion cubic meter slide that is occurring on the flanks of the Revelstoke Reservoir in British Columbia. And that area is impounded by the Revelstoke Dam. So should a failure occur, that would dam the river and impound the toe of the upstream dam called the Mica Dam. So it has significant influence. What you may be able to see in the pictures in the middle is the scarp of this landslide. It's likely has been occurring since the end of declassification 10,000 years ago. You can see the large scarps that are present. And then in the middle, you can see a series of 6 images. And those images show you on the left side, the monitored behavior, and on the right side, the modeled behavior. And so what we're able to do is think about the pre-existing water conditions in that landslide on the top row. In the middle, that's when they've introduced drainage into the landslide. And at the bottom, that's when the drainage is fully active. And so we're able to use the instrumentation data for a landslide that's 0.5 kilometer thick to understand the behavior and understand how drainage is working. So this is a good example of combining the instrumentation, the subsurface knowledge, and the landslide behavior. And with that, we were able to calibrate the model that you see on the top right, which is a three-dimensional model with a series of different nested landslide surfaces. So this is all the work that's being done very effectively. It's certainly not in any way outdated. But what I'd like to show you tonight is how remote sensing can add information to that. So on the left side now we see, this is a photogrammetry model taken by, driving by the slope at 100 kilometers per hour. And then we can build a model from that information. We can map the rock structure, and we can look at things like the slope angle, the ditch position, the kinds of things that go into the classification systems. On the right side, you can see the results of Lidar, aerial Lidar scanning of the Downey slide, the one I mentioned a moment ago. In that case, you can see on the left side the air photo. You can see the scarp of that landslide and the reservoir at the toe. And then from the Lidar, you can see how when we can see through the trees with Lidar, we can really start to partition that landslide, not only with depth, but also spatially. And there's quite significant differences in the way that landslide is moving across that surface. It is a very large area. And so the Lidar data gave us a piece of information we didn't even get from walking over the surface. We couldn't see all of those tension cracks in the dense forest there when we walked over the surface. So this gives us new information about that landslide and permits us to interpret it in a probably more precise mechanistic manner towards the models that Dr. Hook was talking about. So on the left side, we have episodic events where we rank the slopes based on the rating systems, and that helps us guide priority and mitigation works. On the right side, we have ongoing detailed analysis of slope deformation that's recorded by the instruments, and that supports decision-making around risk and around mitigation. So two sort of end members of this environment. So what I'd like to talk to you about today is work that's been going on for 15 years through the Canadian Railway Ground Hazard Research Program. And this is a program that's specifically focused on geohazards and how they affect the over 40,000 kilometers of track we have across Canada. The exposure here is heightened by the fact that much of this construction was done in the late 1800s, early 1900s, at a time when people weren't thinking about geology, and so they were just put in wherever it was convenient. Very diverse physiographic regions across Canada, substantial variability in soil and rock conditions, extensive and deep ground freezing. 3 years ago, the city of Winnipeg was colder than the surface of Mars, and they froze down through all of the infrastructure. And also active geomorphic processes are going on in many of those locations. And you can see the pictures around the outside of that slide showing you from the west coast to the east coast, the varied environments that the tracks run through. So the motivation for this, from the perspective of geotechnical engineers and engineering geologists, is to think about the different hazards that affect the track. So the left two slides show you very large landslides in our western regions in the plains and coming into the mountains, so very large, active, slowly moving slides. The middle two pictures show you rock slope failures. In the upper case, having overwhelmed a rock shed. In the lower case, the rock shed is still effectively passing the rocks over the tracks. The next row of pictures or column of pictures is of hydraulic erosion, often breaching through culverts that are under-designed, sometimes to do with freeze thaw cycles. And then on the right-hand side, thinking about snow avalanches and ice failures. So all of these types of hazards result in unsafe track at the allowable train speed, and very often also lead to loss of capacity. We have two main rail lines across Canada, so if one of them is destroyed by a geohazard, that means the capacity for the whole country is halved, and so it's a significant challenge and issue. So what I'll focus on today are the slope hazard aspect of this project. Here you can see a couple of the sites I'll be talking about. On the left side, the 300-meter high slopes that I'll start with, and on the bottom right, the 200-meter high slopes that I'll end with in this talk. So what we can see here are some of the types of hazards that impact the track. On the left side, a debris flow event that occurred at night. It was cleaned up within a few hours. There was no damage to the infrastructure, so trains carried on. And on the right side, rockfall events. The top right picture shows you very small rockfall events that are captured by the ditch. But the bottom picture shows you when sometimes those rocks end up on the tracks. And so a significant volume that size and larger can derail the train if it hits that size of rock. So 1 cubic meter is sort of the lower limit on those types of rocks, which will become significant later. So not to say that all the trains are running through unprotected terrain. There's a lot of work that's been done across these 40,000 kilometers of track. Top left side, you can see different generations of rock sheds that have been built to pass the rocks over the track. Bottom left, tunnels going through relatively limited sections of terrain, again being built in the late 1800s, early 1900s. It wasn't a very strong tunneling environment in Canada. Top right, you can see slide detector fences. So these are wires strung between upright poles, and when those wires are broken by an event, it'll set the signals so the train no longer progresses through the area. And then finally on the bottom right, many circumstances where they build barricades. They can be the style of concrete barricade you see there, or the high energy mesh fences that they're situated in this case on top of that large barricade. So these are ways that they manage these hazards. So the questions we have are fourfold in my mind. The first is, in thinking about rock slope instability for these large natural slopes, how do we identify which features may generate the next failing rock? If you look at that slope, hazard a guess, could you even imagine where the next rock might be coming from? How do we observe and measure the potential source zones? How do we know, again, in that slope, where the next rock will come from and what sort of volume? Will it be a small failure into the ditch, or will it be a larger failure onto the tracks? Can we foresee potential failure? Can we detect it as it's about to happen? So this slide shows you the location of a large block that's been detached for about 10 years from this slope. It hasn't moved in the last 10 years, but you can see the size of that back fracture. So it's evident that at some point, maybe in geological time, maybe not in our time, that will probably fail. But so when will that fail? How can we forecast that? And then the final question is, once we've identified a potential source zone, what is the risk to the infrastructure below? And so here you can see some track with the warning fences above it. So this brings me to the outline for the lecture. There are 3 sort of general areas I'd like to cover. The first is how we work with the remotely sensed data, then how we use that to do further interpretation of slope instability. And then the final part is a sort of newer area for us, thinking about slope process models. And at the end, I'll conclude with some ongoing research and then some of the challenges that I see going forward in geological engineering and engineering geology. So first off, collecting this data. We use a series of different tools and instruments to collect this remotely sensed data. On the left side, you can see a Lidar scanner. I'll describe that a little bit more in a moment. And that may be deployed either at a terrestrial level, or the second picture in is when you deploy it from an aerial platform. If we keep moving to the right, the next thing we have is a photography system called Gigapan, which I'll talk about later. We can also do photogrammetry from the ground, or from UAVs, or from helicopters. And then finally, INSAR, which is a remote sensing technique deployed either from the ground or satellites. So those are the kinds of tools we've been working with. And to some extent, because we have these very active slopes, we're able to compare and contrast these different methods and how useful they are for managing these kinds of rock slope problems. So if we look at this picture, this is one of the locations from which we can see the slope opposite from River Terrace, in fact. And you can see that several 100-meter high slope, again, with the multiple source zones for rock falls, and you can see a rock shed in the foreground. So that's the vantage point we generally have. In this next slide, we can see a video taken from a UAV over that area. You can see the track at the base of that slope. You can see the rock sheds that are in place to help pass those rocks over the tracks. You can see the diorite dikes that are protruding from the ground and in fact are the source of a substantial amount of the rockfall events. And you can see the debris channels which are moving down either managed by the rock sheds or in other areas managed by ditches that are regularly cleared. But you can see how sharp this terrain is. You can see that it's difficult to access this terrain, but you can also see a completely different vantage point than we saw from that picture a moment ago. And we get a very different perspective on that. And this was taken by a UAV that was sort of modern 2 years ago, but now it's old story because this stuff changes so quickly in this field. So as I mentioned, we can have aerial perspectives. The red arrow shows you the aerial viewpoint. We can have terrestrial perspectives, the green arrow giving you that viewpoint. And then we can have oblique viewpoints that you see in blue. And very often we need to combine all of those in terms of understanding the terrain. In that last video, you can imagine there were many locations on that slope where you would not be able to see past those diorite dikes, and therefore you would not be able to understand the terrain behind. So you need these multiple vantage points. In addition, you need multiple techniques. So we've been working with Lidar scanning and photography, as again I'll describe in a moment, for data acquisition. And the diagram tries to show you the different ways each of these things can be deployed across the terrain. And finally, we also have a toolbox that includes other types of remote sensing, as I mentioned, INSAR, hyperspectral, and thermal sensors. So we're incorporating that into the approach as well. One of the sites we've worked on a lot is called the White Canyon. This is the slope I showed you earlier on that's 300 meters high and 2 kilometers long. It runs along the CN rail line actually runs along the base of it. It goes through 3 very short tunnels, but for the most part is exposed across its full length of those 2 kilometers. There are some rock sheds which are shown in the blue, which you may be able to see. But the reason this is a really unique environment for us as well is across the river, we're able to access the terrain very easily. And you can see the yellow points where we set up all of our instruments to collect the information that we'll hear about in a moment. And this shows you how often we are able to go to the field. It's a 4-hour flight from where we live, so we're not there on a regular basis, but you can see the times at which we're collecting information, which gives rise to some challenges I'll show you in a moment as well. We have had several generations of Lidar scanners, and that's also something that you'll see as we go through this has caused some differences in what we're seeing. So as we're collecting this information, we're collecting 2 major classes. The first is a detailed visual record. There's no surface geometry in this. This is purely a visual record of the slope. And the way we're doing this is using an SLR camera with a telephoto lens, high quality telephoto lens. The robotic head on the Gigapan setup rotates through and takes, in this case, 190 photos across a pattern with a given amount of overlap. And when it does that, you can then stitch it through into a fully detailed panoramic image that is very useful. So again, no geometry information, but lots of physical information. And so in this next slide, you'll see the slope, the glacial fluvial slope here. So watch that rock. I'm going to play through the way you would be able to work with this imagery. So that is what a Gigapan gives you. So those photos were taken from that far distant environment, but because we have a telephoto lens, this is what we can do with it. So slope we cannot access without generating rock slides onto the railway tracks. We can visualize as if we were able to climb up over that slope. And so what you can see here is silt lenses, gravel and sand lenses right through to the cobbles and boulders. So this has been a very valuable tool in the tool set that we have. And so that's what the difference is in terms of the quality of information and the ability to collect this. So the next is then the information about geometry. So we're using, in this case, 2 techniques to get geometry. And in this case, this shows you the Lidar scanner, one Lidar scanner. What this does is it sends a pulse of laser light out. It bounces off various objects in its direct line of sight, and then returns back to the Lidar scanner, recording information about the distance away from those objects. So in that picture, you can see that one pulse responds from hitting the trees, and the second final pulse responds from hitting the rock surface. And what we really want to know is what's happening on the rock surface. So we have to get rid of the trees, which I'll show you a little later. But these tool sets are very valuable because they give you a fully rendered 3D model of the slope with X, Y, Z points in space. And so this represents the geometry of the slope very cleanly and very clearly. So this is a picture here showing you, again, these slopes I've been talking to you about. This is about 1 kilometer of the slope. And in that case, that model has points that are spaced at 7 centimeters apart. So you need to know the geometry of that slope every 7 centimeters in space. You can see a visualization of that here. This is not a photograph. This is a 3D point cloud where you can see each dot represents something on the surface of that slope. You can see the rock sheds, the railway track. You can see locations where we don't have any information behind objects. So as I mentioned earlier, we need multiple vantage points to understand that, but we can really start to see the detailed geometry of that slope from that model. And you can work around it in the lab and really understand the shape of those objects. The second way we can work with this is with photos that have been stitched together into a photogrammetric model. And in this case, these are photos taken from a helicopter, built back into a model, and now we're doing a fly-through of the model. So here, the points aren't so closely spaced together, but we do have a photorealistic visualization of the rock slope, so we can understand what's happening. Again, you see some patches where you can't get information because of the occlusion, but this does give us a way of inspecting these types of slopes that we cannot access easily in situ. So now I'll move on to the processing of all this data that we're collecting. And so what we want to do is try and understand as much as we can about these slopes. The first is, when we come across a slope that we're interested in, and we have either a point cloud from Lidar or from photogrammetry, that permits us to start to map some of the geological setting. In this case, this is from a photogrammetric model, so we have the photorealistic information. And you can see here a thick sequence of Cretaceous deltaic sediments that have been exposed in these slopes. There are 2 major faults here that are shown in red, and there's in fact a paleo landslide scarp that's shown on the top right with the hatched lines. This is the site of a previous 50,000 cubic meter rock slide, liberated by sliding on those 2 joint surfaces. And you may be able to see on the track itself the equipment that's still there cleaning up following that failure. And so one of the first questions is, what are the joint surfaces? What will liberate the next potential failure? And so here's a close-up showing what we start with. We start with cleaning the data, removing trees, removing areas that don't give us good return. In this case, the reflectivity of black shale means that we can't actually get information from that part of the slope. So you see that white band across the middle of the slope. And you see some locations where we have occluded data. And we also remove the talus because that changes enough that it throws off the data processing you'll see in a moment. But so once we've got a cleaned model, then we can move into working with structural analysis, understanding the major joint planes that are present on the surface, mapping those orientations. And for those who are familiar with them, you can see a stereo net on the left-hand side showing you the orientation of the surfaces that are detected from this model. And this is what we're using then to think about the next potential failure. And also in some work that was actually supervised by Dr. Marinos up there in the audience with a former student of his, thinking about joint spacing of the surfaces that we're looking at on these slopes. What are the orientations? What are the spacing? What is the next potential failure? But a caution here is that these are all line of sight techniques. So any joints that are parallel to the line of sight, we won't see from these techniques. And the reason I got into this in the first case is in 2006, 2007, I saw many stereo nets that only had half the information because people were not understanding. They couldn't see what was not in the line of sight. In addition, the data resolution, even when we have information at 7 centimeters apart at 400 meters away, that's still insufficient information to truly understand the joint surfaces themselves. Closer scans, yes. The kind of scans we're working with, no. And so we don't have information on the opening of the joint or the roughness of the joint. So as with all of these things, field mapping is required. Field calibration of these models is required. You cannot get away from that, and nor would I ever advocate that, especially in an engineering geology audience. So then, Now that we have these single models and we can start to work with them, we've been working now for about 15 years on how to align time sequential models, models that are taken at different points in time, as I showed you a few slides ago, every few months, every few weeks, every day, depending on how often you're there. And what you can see on the left side of this diagram are 3 instances in time where a block is rotating away from the slope and out towards the free face beyond. And you can see there's sort of a colored surface on that, which is the area we're looking at to compare the geometry from time 1 to time 2 to time 3. And as we do this, we're able to really understand how that slope is deforming, what's happening on that slope, what direction of motion. And so in this case now, I'm starting to talk to you about processing time sequential data sets. And so the picture on the right shows you about a 2-week period between previous scan and subsequent scan at a time when they were doing some maintenance on the slopes. In these kinds of visualizations, the sort of red, yellow, green colors are locations where material is being added to the geometry, or where the slope is deforming towards the viewpoint. And the blue and purple are areas where you're losing material from the slope, so the source zones of failures. So this visualization shows you what that looks like. This is at a time when they were doing some work near the track. So the rock sheds, you can see locations where they've removed material, cleaned those rock sheds, that's showing in blue. You can also see on the natural slopes a lot of blue in the middle now. That's where they were doing some blasting to clear up the slope. But higher up on the slope, the greens and oranges and yellows, that has nothing to do with human activity. That's all the natural slope behaviors. So the other thing this technique lets us do is think about how humans accelerate this versus the geological processes that are occurring naturally. And so by combining these 2 data sets, by looking at the time sequential changes and being able to zoom in with these Gigapan photographs, we're really able to start to understand some of the processes occurring on these slopes that previously we only saw as a rock on the track or a rock in the ditch. Now we're able to start to look at them while they're still up on the slope. So out of all of this, we have now a database of about 15,000 significant rockfall events from the last years of working with this information. And what we're doing with the database is putting in information about when failures are occurring, what the location was of the failure, and the volume. Because by looking at the slope before and after the failure, we can make the type of object you see spinning on the bottom left. We can calculate the volume of that, and we can understand the behavior of the rock mass accordingly. So now that we've processed all this data, how do we now start to interpret it? And so the next part of this is starting to then think about how these rocks are being generated. What's the structure of the rock mass? What kind of mechanism of failure is occurring? Is it toppling? Is it sliding? I'll talk more about that in a moment. And also importantly, what is the shape of the rockfall? So now we're able to see it in its source, not after it's fallen to the tracks and smashed into 10 or 20 or 100 pieces. So we're able to see what was the shape before it liberated from the slope. Then we're able to map the geology both from a combination of access, in this case at the base of the track, and also from looking at the photogrammetric models. We can map the geological setting. In this case, we have on the left side a batholith. We have orthogneisses that are cut through by tonalite dikes and diorite dikes. So in the pictures, you can see the sort of bottom right to top left structure. That's all of the dikes that are cutting through this rock mass. And so once we've got a mapping of the geology from the track access and from the work with the Lidar and photogrammetry models, we can now start to relate the locations of the rockfalls to their source zone lithology. On the left side, you see over 2,000 rockfall events recorded on that slope over a 3-year period, and we've divided them on the basis of the volume. So the upper picture, very small volumes that you wouldn't worry about managing the railway track, but you'll see in a moment why they become important. The middle area being rocks that can do some damage to the track depending on where they land, and the bottom picture being rockfall events that very generally do damage on the track. And so we're able to look at those different volume classes, look at the geological setting, and put that together. So in this picture, what we can see is the frequency of the different volume events depending on lithology. And we're able to start to separate which of the lithological origins of these rockfalls are going to be the most problematic, and therefore, when they invest in some more rock slope mitigation, where they should put it. You can imagine with several thousand events occurring every year or two that this is a fairly daunting prospect if you don't have some way of guiding your decisions. And as we carry on, again, with the photography, we're able to then add the bottom two parts of the database here that you see, the source zone lithologies, as I've just shown you, and some idea of the rock strength itself. And so as we build the database, we're able to start populating information that normally we can only gain with physical access to the slope itself. So what can we do with this data? Now that we have the database, what can we do with it? So I've shown you the change detection that gives us the information you've just seen. And what I'm going to show you now is how we can start to interpret individual events. So prior to failure occurring, we can detect, in many cases, deformation. And deformation sometimes for as much as 3 or 4 years. So we start to see deformation, and I'll talk more about that in a moment, but particularly we're interested in what's the magnitude, what's the rate, and also the duration of these events. They're never a straight line. There's always a stick-slip motion occurring with them, and so we're trying to understand how to interpret that. We're also then able, when we see this, to start to think about what's the likely structure behind that moving block, therefore what's the likely failure mode. And that is based on the sliding plane geometry. Then once a failure has occurred, we're able to use the information to look at where rocks have impacted the slope. In the picture on the right, the pink material, 18 cubic meter failure, higher up on that picture. And then you can see below that location several points where there's a pale blue or bright blue splotch on the slope. That's where that rockfall fragmented, impacted the slope, removing small amounts of material on impact, and then deposited at the toe of that slope. So we're able to do a little bit of geological fantasy glasses, but we're able to sort of figure out a little bit what's going on these slopes and try and anticipate where we think the rock blocks have fallen, where they have collected, and what's going on these slopes. And so this gives us an idea about then how the fragmentation is going on. And in addition, the final thing we're trying to do with this is understand deformation thresholds. So once we start to see a block moving, if we have a sense that there's a certain number of millimeters or centimeters of movement, then we can start to forecast thresholds when the next similar failure might start, how much time we might have until the next failure would occur. And so one of the things we can do is track the block deformation in great detail, depending on how frequently we're collecting data. This is a case of a over 100 cubic meter rockfall that occurred above the site of the tracks. So this is one because of the geometry. If you're on the tracks, you can't see the source zone. So rocks just appeared in this case onto the track. And in back analysis, in this case, we were able to look at the geometry of the slope, but also more importantly in this case, the backscarp of that failure. And when we did that, we were able to find 3 main planes that were controlling that behavior. And when we looked at a stereo net analysis, again, thinking about the way that those joints might control behavior, we were actually able to see which joints this block was moving on. So you can see in the middle of that stereo net a series of points that are connected up to show a path that's sort of trending to slightly north of east. So the first part of the failure, it was sliding on one joint, and then partway through the failure, it changed 90-degree direction and started sliding on the other joint. So this is unheard of information normally. We don't know which of the joints are involved in the failure, and therefore it's hard for us to understand what the roughness is and therefore what the thresholds are. So the more we can see this information, the more we learn about these slopes and can start to predict what might happen next. So when we think about this, we're always thinking about what the mode of failure would be. And so here you can see cases where in the left side, these blocks are moving purely by sliding motion, resting on the joints below and sliding down towards the free face. And then in the picture on the right side, cases where the blocks are toppling towards the free face, so tilting forward. And there's a fairly rudimentary visualization here, but trying to show you how the sliding might look from the vantage point of our Lidar scanners in the case of sliding. and then how they would look in the case of toppling. So this is the kind of motion we're looking for in the change detection information that we have. And so here's a case where we observed a moving block. You can see it up on the slope. It's a fairly small block. And what we had initially was the red surface, which is the pre-existing pre-failure surface shape. But looking around that shape, we can see that there's a lot of joints that are dipping towards the open space. And so we hypothesized that that block would be sliding down on the joints that you can see below them. And when we started to see the deformation analysis, the upper row shows you the tilt towards the free face, and the lower graph shows you the deformation towards the free face in sliding. So we can separate this block into how much it's tilting forward and how much it's sliding. What you can see over time in the first couple of measurements is that there was a substantial amount of tilt towards the screen in the winter period. So in Canada, that's our freeze thaw cycles, where we're building up ice behind the blocks and they're starting to tilt forward. That was enough in this case to generate a mismatch between the joint surfaces and to allow it to start to move in translation. And so what we're able to do with this is start to think about, how does a joint surface look? What kind of deformation will occur? So once it failed, we could see the backscarp. So the green and red surface is the plane upon which that block slid. And what you can see is a topography of that surface. You can see two red high points, which were the areas where those joint surfaces were matched. The freeze thaw cycles pushed them apart, and then they were able to slide down with the deformation that you see in these pictures. And so we're able to give some hypothesis about what the deformation is in terms of toppling to allow mismatch of that type of joint surface. And we're also able to think about what the deformation threshold at failure might be, in this case around 4 centimeters. So this kind of information in the cases that we're looking at gives us a lot of information we didn't previously have. Now, no two rocks will behave the same way, which makes our job really interesting and exciting. But if we have 10,000 events in a database, we can now start to get some information about what the thresholds are for these kinds of failures depending on mechanism. And so next, I'd like to talk to you about how this has improved our understanding of slope instability itself. So this is a back analysis of a case. This failure occurred in the middle of the night. This was in year 2 of our work with these Lidar scanners, so we were still developing processes for interpreting data. When my team were there, they stay in a rafting resort right across from this place, and so they heard rocks falling at night, and they went out with a Lidar scanner at night to detect the change that was going on associated with this failure. What you can see in the right-hand picture is a picture from the nighttime with an infrared camera showing you the material that's fallen onto the track. And you can also see that the slide detector fence was broken and gave warning for trains not to come through, so there were no issues associated with this. They worked through the night to clear this up, and 8 hours later, they reopened the track. But this gave us a really interesting opportunity to do a back analysis on a failure at a time when we had a lot of information about the slope. If you look at photos of that failure location, we've outlined the failure location in red here, and if you look at the left-hand picture and the right-hand picture, visually it's quite difficult to really see that 2,600 cubic meter failure, where it came from, exactly the shape. But when we do our change detection, we can see the amount of failure that's occurred. So the purple contour there is a 5-meter loss of the rock slope. You can see a slab of the rock slope fell off in that environment. You can see the accumulation below on the slope. And in fact, you can see the shadow of the excavator, because when they took that scan, they couldn't see past the excavator. And so you see a shadow, in fact, in the model in that instance. We could quickly do some work with this change detection to understand the formation of the failure. You can see on the left side the pre-existing surface in cross-section in white and the post-failure cross-section in yellow. And this exposed a dipping joint surface that had not been observed before, even at track level, that had caused this failure or permitted this failure to slide down. When we start to look at this information, again, early on in our process with this, we realized that there had been 2 relatively substantial volume failures in the preceding months to year. Those are shown in yellow and red on the diagram on the right. So we started to do some back analysis, and when we did so, we realized that there had been 16 different events that may or may not be related to this particular event. So the big yellow blob in the middle is the eventual 2,600 cubic meter failure. But when we looked back and analyzed the data we had before this, we were able to determine a few things. The first is, early on in the preceding winter, fall, winter, the large red block, 128 cubic meters, fell. So that was the first indication that something might be going on in this area. This could in fact be the end of it, or in this case, it was the start of it. So then, over the winter time, a whole series of relatively small blocks, ones you normally wouldn't worry about, failed all around the base of that eventual failure. So what can you tell about that? You have a bunch of small blocks that you don't normally worry about. They're now starting to outline the base of this failure, eventual failure. Then later on in the springtime, as the ice was coming out of the rock, the pale green or pale blue failure occurred. That's about a 1.8 cubic meter failure, nothing really big. And then a whole series of failures occurred along what turns out to be a shear zone on the backscarp of this failure. So in hindsight, we can understand what was going on. Foresight, we couldn't, because there's too many small failures here that it's hard to know which ones are important. So it's great to be able to look in hindsight at this, but this gives rise to another avenue of research that a number of groups are working on, thinking about precursor events and what they can tell you about the engineering geology of the slope and the failure mechanisms. Around this time, we developed some techniques to really look in detail at the deformation of these slopes. And you can see here from left to right across the top and then across the bottom, over time, the way this block was moving towards the free face. Again, in hindsight in this case, but you can see from this information that we're able to really discern how this block is moving. On the right side, you can see a series of graphs showing you the deformation in time, the accelerating deformation, and the magnitude of the deformation before failure. All of those lines represent different positions on that block, with the highest line being at the top of the block because that was doing the most work in this case. So this was a case where hindsight really gave us some knowledge about how to start to work with this data. So then going forward, we want to understand how to use that to now start to communicate potential slope instability. So the next case is this one. This was the 50,000 cubic meter failure I showed you earlier. About a year and a half after that failure, they built a new rock shed. You can see that at the base of this slope. And that rock shed was designed so that blocks would fall onto it gradually load it, gradually get to the point there was enough talus present that the rest of the rocks would flow over into the river valley below. This was not intended for any large-scale failure events. And what you see from our Lidar scanning is potential large-scale failure events. So 50,000 cubic meters has just fallen off this slope between the two fault zones I showed you earlier. And now this slope is gradually unraveling and progressing towards a more stable environment. We detected the three areas you see, A, B, and C, across the slope that were deforming. In the case of B and C, deforming 4 centimeters in the 8 months after this was built. And in the case of A, deforming 8 to 10 centimeters in the months after this rock shed was built. So when we looked at this, we realized that over the summer into the fall, it was fairly stable, but then in the fall, it started to accelerate again. That's the row of pictures on the right side, or sorry, the column of pictures on the right side of this diagram. This is the deformation that had occurred by November of that year. So we realized that in looking at the structure, we probably had about a 4,000 cubic meter failure about to occur in the yellow block area. And so we gave warning. We said to the railway companies, you potentially have a 4,000 cubic meter block and you have a couple of other locations. Is your rock shed designed to withstand that? And in fact, during our sponsors meeting at lunchtime, everybody's phone rang and there had been a failure. It was very good for our funding, actually. But you can see in these pictures that the rocks had fallen onto the shed. And the reason it was reported was that some rocks had bypassed the shed on the right side of this image, and the track supervisor saw rocks on the track. So that's when warning was given. We went out the next day and collected information, and we determined that, in fact, the volumes we had predicted based on the structure were fairly close to what happened. The analysis they did to think about the rock shed indicated it probably wouldn't be damaged by those events. you can see a fairly substantial volume accumulation on top of that rock shed in green there. And in fact, if you can see it, the rock shed has some sort of green deformation towards the viewpoint. So in fact, the rock shed did deform a little bit in response to this impact. This was designed so that if roof panels became damaged, they could replace them, which they had to do in 2 places. But they also realized they needed, from this imagery, to extend the rock shed on the right side. It just wasn't wide enough in that location. You can see where the rocks went over, and you can see that that's just going to continue to get worse as material fails down. So then the final part of this section is, how can this information help you with decision making? We've just had one example of that. But what we've been doing is looking at these models, looking at the information we can gain about precursor information, and we're able now to start discerning where a rockfall might occur before it does. So on the upper middle part of this picture, you can see a section which has got arrows pointing towards us, and we've identified those pale blue sections as rockfalls that are precursors of a potential bigger event, outlining it like we saw a few moments ago. And so the other thing we've discovered through this work is that when these rocks fall, as I said before, they don't fall as a single entity. They very often break apart. So what we're able to do with the Gigapan information is map the structure and figure out ways that those blocks might break apart in their passage. The picture you see here is of the rockfall event that occurred on the left side image, where again we could get some sense of the fragmentation of the block based on the locations where the fragments impacted the slope. So we've mapped structure onto the block on the right-hand side, and then we're going to use a technique for modeling. So the technique we're using here is physics engines that are built for games or videos. The reason we're doing this is that these physics engines move at extremely high rates. They have enormous amounts of money behind them in their development, and they're physically rigorous and correct. So these provide rapid simulation of rocks, both the fragmentation and the impact of the rocks. And they also let us build realistic world models very quickly. So in the early days, my students in the lab were playing with Minecraft, which most people don't want their kids playing with, but in my case, they were playing with Minecraft, trying to learn how to build these models from our Lidar data sets. You can see a realistic model there built from the Lidar data set, and you can see the location of that rockfall that we think is going to happen based on the precursor events that we've seen developing around it. So here you can see the simulation using the game engine. You can see the rock fragmenting on the pre-existing structure we've mapped from the slope. In this case, these are all fragments of a fairly similar size. If you watch them, you can see them impacting on the slope, in some locations accelerating, in some locations slowing down. In many locations, they come to rest, and then they start again when they're impacted by another falling block. So we feel that we're starting to get to more realistic modeling of the way rocks behave on slopes from doing this kind of work. And so you can see that in this case, we've had the source zone evacuated. We've had some blocks come to rest midway on the slope. Some blocks have come to rest on top of the rock shed, and many more of them have ended up in the river below. So in back analysis now, we can look at the change detection, understand the volume of that event, understand more about the backscarp and the structure that was present in that rock slope, and we're able to look at the photographs to understand the geometry of the slope, pre and post failure, both up on the slope and in the deposition zone. So we're having a sense of the size of fragments that are remaining on the slope in the top right picture and remaining on top of the rock shed in the bottom right picture. So we're able to start, at least visually, to calibrate these models. This is the result of the modeling. So the left side is the change detection results, the source zone in blue with, again, the material that's been deposited on the slope and on the rock shed. And on the right side, you can see the result of that simulation. And for now, we're able to say that we're doing fairly well, I think, in terms of matching the volumes that are remaining on the slope and matching the volumes that remain on the rock shed. These tools are evolving rapidly. So a couple of days ago, they created a new model that lets us model 1,000 times more blocks than you just saw. in less time. And so as time goes on, because of the push from the game engine companies and the movie companies, these physics models are being changed every few months. And so in the end, the possibilities become limitless. But we can't just rely on looking at volumes. We have to think about the geology. We have to think about the structure. We have to think about how this is behaving. And so one of the other ways in terms of the decision-making we can work with this is modeling the locations where source zones, as you've just seen, may occur and where a deposition may occur. This is another case where we did some forward analysis of a moving block, and we were able to see where blocks might come to rest on the slope and where blocks are likely coming to rest in the ditch and also on the railway tracks beyond. So the red material here is contained, about 95% of the volume is contained within the red shaded blocks. The blue shaded blocks spread out over the tracks are about 5% of the volume that was projected. So we're coming towards the idea of being able to say there's a 5% volume, it's a probability that 5% of the volume will end up on the track area. So you need to do something about this before it occurs. On the right side, you can see the results of that visualization. You can see the pre-existing slope surface shown with a dashed line in the diagram to the right. And you can see the eventual surface shown in the dark line. You can see where the dashed line is above the dark line, those are zones of loss. And where the dark line is above the dashed line, zones of accumulation. And what we're mostly interested in is the accumulation that's occurring in the red shaded section, because that's where the railway tracks are. And so as we're able to calibrate and build these models, we're being able to start to think about not just a single rock bouncing down the slope without any fragmentation, but we're able to start thinking about where will these fragmented blocks end up, and what does it really mean for managing these tracks. So now I'll move into the final part of the series, the lecture here, which is about slope process models and the way we're using this combination of remote sensing and enhanced understanding of slopes to now come to process models. So first off, developing them. Process models, in my mind, provide a detailed and calibrated basis for modeling these slope changes. What do we learn from this information? What can we do with it? And in particular, we need to move to thinking about what are conditioning and triggering events that are occurring on these rock slopes. As you hopefully have seen, this sustained remote sensing data collection lets us look at change and lets us to look at the geometric relationships between different scales of events, looking at the frequency of events, and looking at precursor events that give rise to large-scale failures. You've also seen that we can assess deformation and relate that to structure that suggests to us a failure mode and suggests to us a threshold for warning. So as we move through these models, the idea is that using this information, we can now start to have a mechanistic model that's founded in geology and founded in recorded information. Here's the White Canyon rock slope again, one part of it, kilometer of the slope track, or the slope with the track below. And what I'm going to focus in here is on the purple rectangle at the base. But this is a slope over the period of time shown there that again had over 2,500 rockfall events, most of them with no influence whatsoever on the track. So for the railway track operators, most of these events are insignificant. But for us, as indicators of failure modes and mechanisms, they become very important. So if we focus in down here on the cut slopes near the track, we can see another rock shed on the top left side. You can see tonalite dikes cutting through the ortho-gneiss. And you can see also in darker color the diorite dikes cutting through the ortho-gneiss. You can see one of the trains going through to give you an idea of the scale of this. Over about a 4-year period, you can see the change detection that's occurred on that slope on the bottom left picture. So that's showing you that about 80% of that rock slope surface has in some way or another failed over the previous 4-year period. Again, something that the railway track operators had no sense of because most of these are not significant enough to cause an issue. But you can see in that histogram diagram that a number of these events are in fact in that larger volume, which is significant for the track operators. So how can we use the smaller scale information to predict the larger scale events that might occur? So again, looking at the slope processes, we're thinking about the structure. And what you see on the top left diagram here is again mapping of the structure that's present on that rock slope surface. from the perspective of the Lidar data sets. You can imagine that with only 2 railway tracks in Canada, it's almost impossible to gain access to track. We rarely actually get that, maybe once every 2 years. And so lots of times our models are built initially from this process and then verified when we can gain access. You can see again, for those who know about stereo nets, the structure and the slope orientation. But in this case, what we're really focused on is this. You can see in this diagram those same rockfall events shaded by the season in which they occurred. So the blue colored events are ones that occurred in winter, and the red colored events are ones that occurred in summer. So now you're starting to see in this case that there is a very strong likelihood that most of these events will occur in winter. Again, heavy freeze thaw cycles, precipitation is higher in these mountainous areas in the winter. And so it's logical that this is the result, but can we do more to understand these behaviors? Can we do something to start thinking about what kind of rainfall events or what kind of freeze thaw events might lead to failure in the future? So we can look at the weather data shown across the bottom. In red, that is the temperature, and in blue, the precipitation. The middle diagram, however, is the interpreted version of that we're working with. So here, we simplified the weather data so that you can see cumulative progression of information over those years. In red, the number of freeze thaw cycles. So you can see in the winter months, freeze thaw cycles accumulating, and then of course in the summer, usually not. So the lines become horizontal in red in the summer, start to accumulate again in the winter. And you can see in blue the rainfall. So the rainfall, you can see steeper gradients in the winter months. Some rainfall in summer, but most of it's occurring in the winter. So this is the environment in which these rockfalls are being liberated. When we then look at the information you've seen graphically a moment ago, now plotted as you see here, you can see in black the number of rockfall events that have been occurring, and in green you can see the volume of rockfall events. So you can see from this that the number of rockfall events has been marching along. In the early period of this, it seems to march along fairly well with the weather, but in the latter half of this diagram, there's a change in the behavior. And so this yellow oval shows you what we're interpreting as a change in the way this slope is responding. So if we look to the left of that in the earlier period, again, we see this accumulation of freeze thaw cycles, which are significant in that they're frost jacking the blocks. And you can see that over the winter and summer, there's sort of an accelerating, decelerating behavior of these blocks. Then after this period of time when a large series of events occurred, and you can see on the bottom diagram on the right, the number of rockfalls that occurred over that winter. Almost the entire slope had some rockfall behavior occurring during that time. And you can see that change in the curves. You can see the jump in the volume, and in fact now an acceleration in the number of rockfalls per year. So when we look at this in detail, we discover that before that change, there were about 7 freeze thaw cycles every year, roughly, on average, and about 200 rockfalls every year in that zone. After that time, in the last 2 winters, we've had about 15 freeze thaw cycles every winter, and now we're seeing almost double the number of rockfall events. So in back analysis, we're starting to understand how these freeze thaw cycles affect the volumes and types of behavior that might occur. So now I'd like to move on to calibrating these process models. Again, this is the glacial outwash deposits during the Quaternary period. Here you can see the Lidar models in plan view on the top left and the cliff view on the bottom left. And what you may be able to see from your seat even is the fact that there are the cobbles and boulders that I showed you in that Gigapan visualization near the beginning of the lecture. And so one of the questions we have in this is, how do all these different layers affect the behavior that we're seeing? We see over time that lots of the behavior in the upper picture is concentrated on various layers. You can see horizontal patterns in that blue loss plot, showing you the locations where failure has occurred. The lower picture shows you the sequence in time of when those occurred. And you can see there's a pretty significant event that occurred in bright pink shown there. So across the slope, large sections of the slope were affected during that period of time, again, a winter time. And so our question here, this is outwash material, it's not cemented, it's cobbles, boulders, gravel, sand, silt. And so our question is how are all these materials involved in what we see on this slope? Are the boulders and cobbles armoring it? Are they protecting the slope? Are the silt clay layers creating perched water tables? Are they locations where water might be seeping out and preferentially eroding the slope from below? And does the talus buttress the slope in any way? Is that something we can use temporarily, at least, to help solve some of these problems? The bottom right picture is a compilation of the Gigapan imagery shown in the inset, and then the Lidar model, and we can match up what we're seeing in the Gigapan with the Lidar. And when we do that, we can see the locations on the slope where we have the slope protruding out and where we have talus resting on it. So shown on the left side are colors, the green being the talus, the bright orange being locations where there are boulders to cobbles, and the blue being locations where we see silt clay layers. So what's happening on this slope? How are these different layers affecting it? And you see in the diagram on the left side in section, the change in that slope from the spring of 2013 to the summer of 2019. So over 6 years, a little over 1.5 meters of loss from the surface of that slope. And so when we start now to look at the change detection data in this section, small section of the slope, only 6 meters of slope here, but we're starting to try and understand what's happening. The times we took information, and as this progression plays, you'll see when data was taken, whether it was winter or summer. So if you watch on the right side, you'll see the generation of that slope. So you see times when there are sharp corners, times when that's lost and the slope becomes much more shallow, times again when there are sharp boundaries on that slope. And so what we're interpreting that to be is that cobbles temporarily stabilize the slope. They hold back material, but then those become undercut by the water flowing on those silt layers. So in some locations on the cliff, you see quite an indent below those cobble layers. And then when they fail, they permit a lot of accumulated material above to slide down into the valley below. So we're starting to develop an understanding of how the processes on this slope will respond to temperature and weather. This then brings us to machine learning. So because we've identified the fact that the cobble sizes are the ones that are the most important here in terms of the big scale slope behaviors, we want to identify automatically where those materials are. So in this picture, you can see a machine learning program called Canupo, which has been used to identify in blue, cobble sizes and larger, and in red, the cobble sizes and smaller. And then the next one, we can see a comparison between the photography and that interpretation to get a sense of how well it's working. And here we see another type of technique called a random forest technique, where we're able to identify the cobbles on the cliff surface itself. So now that we can identify these automatically, we can now start to map where some of these processes are likely to occur. So that's where we're talking about building, calibrating these process models. So the final part of this now is thinking about forecasting in these slope process models. So the final example I'll show you is this. These are debris flow events that have occurred over time. On the left-hand image, there was a substantial storm on this slope in 2017 in the fall. And almost every debris channel on that slope completely flushed and emptied onto the track. So you can see the red piles of material at the base of the track in this location. One of the reasons this is important is that when you look at a debris flow in these kinds of models, you have no sense of where the base of that debris flow is. You don't know how much material is accumulated on the slope. So at time one, you've got a surface, you don't know what it is. Time two, which occurred in this case in November, storm, shows us the bare rock at the base of the debris channel. Then time 3 and time 4, we start to build up debris again as rock falls occur and accumulate in that basin. So the question now on these process models and the calibration is, how much material do we need to build up in that channel? How much will be required before it'll flush again? And what combination of either rockfall or storm event will cause that to happen. So here we're now starting to think about calibrating these kinds of models. You can see here it's the volumes that build up and flush, build up and flush in one of these debris channels. So we can now establish in that particular channel's case about 150 cubic meters of material. The next time there's a storm, it'll flush. So it starts to give us some idea of how to manage these slopes. And we can look at precipitation related to the amount of material stored in the channels and the amount of material falling into the channels and start to make some hypotheses about these techniques. So the final two sections here are the ongoing research objectives. In this case, one of the things that we're continuing to do is think about how remote sensing data can help us. And in particular, we'd like to have more continuous information. When we have 3 or 4 or 6 months in between events, it's hard to interpret the details of what's been happening. So what we're working towards on the next phase of this project is some more permanent setups. There's a process being developed at Colorado School of Mines thinking about permanent camera setups, Doppler radar or ground-based INSAR to give us more continuous information about these environments. We are working on improving the automated data processing. You can imagine that this material takes a lot of time to work through, and so these processes are being automated. And in particular, we're trying to detect and extract rockfall shapes and volumes directly from the point clouds once we've got them cleaned sufficiently, and working on mapping grain size distributions to understand how the slopes are evolving. We are also considering as we go on, as our data sets get larger and larger, that we have the opportunity to apply increasing numbers of machine learning techniques, but always considering slope process models, including thinking about failure mechanism and thinking about the engineering geology setting in which we find ourselves. So here's one example of some of the ongoing automated data processing. This is a paper which has just been published where we are automatically detecting and extracting the trees from the point cloud. Previous to this, my students sat there and individually removed every tree. So you can imagine that they weren't very excited about their work for short periods of time at least. So this technique lets us really think about how to remove the materials that are above. This is challenging though, because sometimes large rocks have the same morphology as a tree to a machine learning system. So we have to keep track of this and really think about this. And then also continuing to work with the game engine physics. This is a new one called Houdini. You can see this block fragmenting. So this is self-fragmenting as it falls down the slope, and the individual particles may may fragment upon impact as well. So this was released about a month ago, this tool, and my student who's working with this was way faster to build. So as I said, these kinds of techniques are evolving, and this is going to give us a lot of new opportunities. But most important is the line at the bottom of this slide, that we have to use validation cases from our slope monitoring work in order to understand that we are, in fact, building a model that's realistic. In conclusion on these, I think you'll see that these repeated scans of the rock slopes permit us to detect small precursor changes, permit us to detect sub-centimeter deformations, and they let us forecast, in some cases, impending rock slope failure. And I think you'll also have seen that being able to look at identifying volumes across a wide range gives us a bunch of opportunities to look at precursor events through to large-scale events and really start to understand these models that Dr. Hook talked about at the very beginning of this lecture. In conclusion as well, I think you'll have seen, hopefully, that these models we have to think about how we develop them and build them. We need multiple vantage points. Very often we need multiple tool sets, and we need time sequential models to detect the kind of information I've shown you. As I've mentioned, these are techniques that are rapidly evolving. When we first started these projects, our data took about 2 hours per section of the slope. Now my students can do the entire slope in about 2 hours, because now these equipment are collecting data at 1 million points a second, basically in terms of the rate at which these Lidar scanners are moving. We have new techniques to build these data sets through the automated processes and software and visualization tools to display the data. I haven't talked at all about data visualization, but that's another enormous area of growth and potential, as the previous speaker mentioned. And this is a very fascinating new area to be working in. We've understood better the events that are occurring. My students are all insistent on, as am I, that this is done in open source environments so that anybody who wants to work with these tool sets can do so once the thesis is published, so everybody learns together. We can do this at different levels of data quality. In fact, everybody with an iPhone here could run around the room and build a 3D model of this room in about 10 minutes. And we can also build these databases that permit us to go forward on the analysis of failure modes and warning thresholds. So the final part of this is what I see as the future opportunities and disruptions to our practice. Across the top, you see the visualization techniques that I mentioned earlier that I haven't spent any time on here, but the ability to communicate geological interpretation and geological information from maps through to the 3D visualizations that we've seen from the British Geological Survey and that we see from companies like BGC Engineering. These are areas where we have an enormous opportunity to communicate amongst ourselves, but also with the public in a very different way. On the top right, you can see the idea that as we get more information, we can get into the machine learning techniques. Again, always with the caveat that we have to keep the engineering geology in mind. Across the bottom, we see the challenges and disruptions that we see already. We see extreme events that are challenging us, and we see climate change, which is challenging us. And I think in our case, very often we've looked to the past to understand the future, and now we're seeing rates of change and behavior that's unprecedented. So it's harder for us to understand where the next threats and opportunities, as the previous speaker mentioned, exist. So how do we get multidisciplinary teams to work together? How do we get people to find common understanding? I'm finding now that I'm educating people who have been digital their whole lives. How many of you came here tonight using the paper map at the top or using your iPhone at the bottom? We lose physical reality when we use our iPhone all the time. We don't look at the landmarks. We don't understand the geometry that we're walking through. If you spent your whole life being digital, then you don't have an innate sense of the physiography and geology around you unless you're really looking for it. And so this amount of information is both good and bad, but everybody needs to be aware that that's the case. How do we ground truth? How do we continue to have a competency in engineering geology where in many cases the field work and the lab work is being cut because of budget cuts? How do we continue to keep the ground truthing capabilities of the people entering our profession where they should be, that experience? What can we do with large data sets? We have these opportunities with machine learning, but we always have to keep the engineering geology component in mind. And finally, as I said a moment ago, climate change is changing the change we see, and so how do we start to use that, thinking about back analysis through to forward analysis? I have a few acknowledgements before I finish. The first is the project that I've spent a lot of time discussing tonight has been going for 15 years, and we've just proposed another 5. This is a unique project in that it includes both the main railway companies in Canada, as well as 2 universities ourselves and University of Alberta, the Geological Survey of Canada, but also Transport Canada, who are the regulator of the railways. So this is an environment where private railway companies, universities, and the regulator have been together for 15 years doing this kind of research. I've had many students working specifically on this project over the years, and you can see the names of them here. A number of them have worked with me either as postdocs or PhD students on these rock slope areas. But as Christophmus said at the beginning, I've supervised over 30 students. So not shown here are all the other ones who've worked in the lab on other problems who've also contributed immensely to this program. Finally, my life acknowledgements, my entourage, as was mentioned in the ground engineering article. My entourage includes my husband, Mark Diedrichs, up there, who has been part of my life from the beginning, and my kids. Thanks.